Okay, so previous day we have discussed BJT amplifier introduction. All of you have heard that video. Okay, so now from onwards we will discuss the different transistor model, and this transistor model, the transistor in the circuit will be replaced by this model, and we will try to derive the different characteristics of the amplifier that we have discussed. Different characteristics mean these are the characteristics: input impedance, output impedance, voltage gain, overall voltage gain. Like this parameter we will try to derive from that, replacing the transistor with the model and connecting the other parameter in the circuit. Okay, so the first model we like to discuss is the Ebers-Moll model, and this is the best model perhaps. The all operating region of the transistor can be represented by this model, but there is some sort of disadvantages also and some sort of advantages also with the help of this model. So whenever we try to model this Ebers-Moll model, this Ebers-Moll model is a simple, okay, I'm just changing the color. So this is your transistor, NPN transistor. I am considering an NPN transistor. Okay, now this NPN transistor, okay, so this is NPN transistor. NPN transistor will be replaced by two diodes. This NPN, these two diodes. Okay, two back-to-back diode. Okay, so this is NPN transistor. This is your emitter, this is your collector, and this is your base. There is two diode is there. This is diode D, suppose this is diode D1, then this is diode D2. Okay, two back-to-back diode. Now whenever we want to this is the internal model, that means the diode equivalent model of the transistor. So is the Ebers-Moll model. This is the model actually. Okay, now if we want to replace, internally we assume that inside the transistor there is two diode. Okay, this is the first thing. The second thing is that whenever you want to model or you want to draw the transistor in the equivalent thing, then we draw this like this, in this way. Suppose this is diode D1, this is diode D2, two back-to-back diode, and in through this diode the current is flowing through. There is a current flowing, and there is a current flowing also through this diode. This is your changing the color. This is your emitter, this is your collector. Okay, and now this is your base. The base current is your IB current. Okay, this is your IB current, and this current is IED. Okay, current flowing through this diode is IED, I am assuming, and current flowing through this diode is ICD. Now what happens, this is emitter. Now from the emitter to base, this is your base terminal. Now from the emitter to base there is a flow of carrier in the NPN transistor, as we are assuming the diode in the forward bias direction, so there is a flow of electron. Now as there is a flow of electron, this current, this emitter to base current, okay, whatever current is flowing from emitter to base, some fraction of the current, because in the transistor all of you know that the some fraction of the emitter current which are entering from emitter to base is actually reaching the collector. Okay, so some fraction of the emitter current is reaching the collector. So that means this current, this IED, okay, this IED is actually, this is a dependent current source is there. This is collector. Okay, so this current is alpha F IED. Why this is alpha F IED? I hope you know that, because this current, this is the forward biasing current, emitter to base. This current is, some portion of this current is reaching the collector. Okay, so that's why there is a dependent current source here. Now if we just consider the transistor in the reverse direction, that means the reverse active mode. In the reverse active mode, the emitter and the collector operation are just reverse. That means if there is a flow of carrier from collector to base, then some portion of the current must reach the emitter. Okay, so that's why there is also a dependent current source is there. And okay, and this current is fraction of this current. So this is the reverse current gain and ICD. This is to, these two are the same concept. That means whenever there is a current flow from the emitter to that means emitter to base, then fraction of this, some portion of the fraction of this current is reaching the collector. That's why these two are related. These two are related. And if we just reverse the transistor action, then what happens is that the some portion of the collector current, if we assuming that the collector base junction is forward bias, then some portion of this current will be reaching the emitter, just the opposite action. Okay, so that's why this is the Ebers-Moll model. Here we are assuming, first we are assuming that inside the transistor there is two diode, back to back connected diode, but current of this in this diode is reaching at the collector, and current in this diode, if there is a flow of current, that is also reaching in that direction. So that's why there is two dependent current source here, and there is one dependent current source here. Okay, now alpha F is the forward current gain. I have said that the alpha F, this is the forward current gain, and alpha is always less than 1. Alpha is the forward current gain, which is less than 1, and alpha R is the reverse current gain, which is also less than 1. Okay, this is the two thing. And now if we want to calculate the current, that means the IE, emitter current. Okay, now the emitter current direction must be in that direction. Now the emitter current is IED. From the current from the model, you can know that alpha R ICD. Okay, emitter current is IED minus alpha R ICD. Okay, from the, if we just apply the KCL at this node, then we will get the current. Now IC is also represented as alpha F IC. So IC is in that direction. Okay, so IC is represented by alpha F IED minus ICD. Okay, so just look into the diagram and apply the KCL, then you will get this two current. Okay, so this is very simple. Model is also very simple, and why we have used two dependent current source in the model, that is also clear from the transistor action. Okay, so I think up to this clear to you. Next, IED. What is IED? So IED is the, there is a diode connected, so that current is your IED. So as this is a diode, so current equation of the diode is be valid here. So I is 0 e to the power base to emitter voltage divided by eta Vt minus 1. So this is the ordinary forward bias diode current equation. And ICD the same, we are just reversing the emitter and the collector terminal, so that's why IC 0 into, this is the reverse saturation current, e to the power, and that is happening at the collector to base junction. So the voltage is base to collector, VBE here is your VBC minus eta Vt minus 1. So this is the two current IED Okay, IED, ICD, and IE and IC. IE and IC can be calculated, the KCL applying here and also KCL applying here, and IED and ICD is just the diode forward bias current. Okay, so I think up to this clear. Next, if we just simplify further, then IE is nothing but, so this is IE. I am just replacing IED with this equation and ICD with this equation, then we get a complete picture of IE and IC. Okay, so your IE is nothing but IE0 e to the power VB divided by eta VT minus 1 minus alpha R ICD. So ICD will be replaced by this equation, so IC0 e to the power VBC divided by eta VT minus 1, and IC will also be represented as the same way. IC is nothing but alpha F IED, so alpha F IED, so IED is IE0, this is IE0 e to the power VBE divided by eta VT minus 1 minus, and ICD, so ICD is IC0 e to the power VBC divided by eta VT minus 1. Okay, so these are the two complete picture of the current equation IE and IC from the Ebers-Moll model. Okay, so this is the expression for IE, and this is the expression for complete expression for IE and complete expression for IC from the Ebers-Moll model. Okay, so this is the Ebers-Moll model. We have replaced the inside the NPN transistor with the two back-to-back connected diode, and then what happens, we just replacing the transistor concept. That means if the forward bias current in this diode is there, so some portion of the current will be reaching here, so that is represented by this dependent current source. And if we assume there is a forward current in that direction from the collector to base, then some portion of this current ICD will be reaching here, so that is represented by alpha R ICD. And from there we are just writing the this 4 equation based on the diode concept and also transistor concept. Then you get a complete picture of what is the value of IE and IC from that Ebers-Moll model. Okay, now Ebers-Moll model, the most important point of the Ebers-Moll model is that it is valid, okay, for all operating region of transistor. This question comes often, for all operating regions of BJT. Okay, there are 4 operating region in the BJT. That means the active region, saturation region, cutoff region, and the reverse active region. All these 4 region will be represented. All these 4 region can be represented on this Ebers-Moll model. Okay, with the help of this Ebers-Moll model. So that's why this model is, there is no other good model than the Ebers-Moll model. But there are some drawbacks also. That's why we are not using this model in our transistor whenever we want to analyze the transistor with the help of the model. Okay, now if we want to represent the active model with the help of the Ebers-Moll model, now how do we represent that? In the case of the active region of the transistor, suppose emitter base junction, there is 2 junction in the transistor, emitter base junction, that is in the forward bias, and in the collector base junction, that is also reverse bias. Okay, so this is, I am just showing you one region how it is being represented with the help of this Ebers-Moll model. Then you can easily represent the other 3 region of the transistor with the help of this model. Okay, So the active region of the transistor, their emitter base junction is forward bias and the collector base junction is reverse bias. Okay, now how it will be represented? Now as the emitter base junction is forward bias, you can say this is forward bias, so this diode will be on, and this is reverse bias, this diode will be off. Okay, so there is no current and there is the reverse bias, this diode is reverse bias, that means this diode you can see as open circuit. Okay, so I'm just replacing this. So you just, this diode will be on because this is forward bias, and this diode will be off because this is reverse bias. Okay, and this is base, this is collector, and this is your emitter. Okay, now what happens, this current is your IED current because this is the forward bias current. So as this current is 0, okay, so this current means ICD. So ICD equal to 0. As ICD equal to 0, the dependent current source that is dependent on ICD, that is of no use. So the ICD dependent source happens to be here. Okay, that happens to be here, that is of no use. But IED is there because the forward biasing of the emitter base junction, as the active regions, emitter base junction is forward bias, so IED current is there. So the dependent current source that is dependent on the IED, that will be there here. Okay, so that is present here. Okay, and that is your IC, and that is your alpha F IED. Okay, so this will be your open circuit, this will be not present because ICD equal to 0, so alpha R ICD is of no use, and ICD is also 0 because this was reverse bias and this is your forward bias. Okay, so this is the complete picture of the active region. This is the complete picture of the active region of the transistor that can be represented. So here your IC will be equal to your IC. What is the IC in this case? In the active region, in the active region, all of you know that the emitter current that will be flowing in the transistor, some portion of the emitter current will be reaching into the collector. Okay, so here's the emitter, the diode connected at the emitter region or the emitter junction is current flowing through is IED. So that's some fraction of the current, that means the alpha F IED, that is here. So you can also apply KCL here in get that. So alpha F IED, so that is the current that is in sync with the transistor concept, and the emitter current is totally represented by IED because this current is absent. Okay, IED, forward bias current, and IB is nothing but IE minus IC. IB is nothing but IE minus IC. Okay, so that is the case. So you can see here that how beautifully the transistor in the active region can be represented with the help of this Ebers-Moll model. So that's the beauty of the Ebers-Moll model, that every region of the transistor, each and every region of the transistor can be represented with the help of this model. Now the advantages and the drawbacks of the Ebers-Moll model. Now I am writing the advantages. Advantage number 1, that all operating region can be represented with the help of this model, that I have also mentioned at the starting point. So all operating region of the transistor, that means the full operating region of the transistor can be represented with the help of this model. And second advantage is that any bias and temperature, any biasing condition and any temperature, it will be valid, this model is valid. And disadvantages, there is two main disadvantages, that it is a non-linear model, that is the main disadvantages. Okay, it is not a linear model, it is nonlinear model. Why nonlinear model? Because we are using the nonlinear device. Nonlinear device, that means the diode in there. So the superposition principle of the linear circuit operation cannot be applied here. That is that means network analysis, you want to apply the superposition bilateral linear network in the any kind of network analysis. Whenever you just read out the network theory or the different network theorem that is written at the first line, that this theorem is valid for the any bilateral network. Okay, linear bilateral network. So linear network, linear, as long as the circuit is represented by the linear circuit element, then you can apply the superposition principle or other network theorem in that and can simplify the circuit. But here, as this is a nonlinear model, you cannot apply the linear circuit operation or the linear circuit theorem here. So that is the main disadvantages. You cannot simplify the circuit further, and the diode are being used. So that is the two disadvantages. Okay, so that's why we are not, as the model is very good. There is you always remember that there is no other better model than the Ebers-Moll model, but due to these two disadvantages associated with this model, we are not using that model further. Okay, so hope you understand all the concept. So the summary, in the previous two lecture we have discussed the AC analysis, how AC analysis is being performed, the steps towards the AC analysis. That means first step is ground the DC supply. That means the transistor AC analysis, we are just model the transistor with the help of the different model, and just by applying any kind of AC signal and how it is behave, input output resistance and the voltage gain for the calculation of this purpose. That is the main purpose of the AC analysis. Now the steps towards the AC analysis is something like this. The first step is the ground the any circuit, ground the DC supply, short circuit the capacitor, and third point is that replace BJT with this equivalent model. So we will learn the BJT, because Ebers-Moll model is no longer, I have said that the replace the BJT with equivalent model. Okay, so we have learned a model, but we have also seen that this model is no longer can be used in the any kind of analysis, any kind of AC analysis, because this model has some sort of disadvantages due to the nonlinear element present there. Okay, as there is a nonlinear element present there, you cannot linearize the circuit. That means the linear circuit elements is the resistance, capacitance, like that, and if these elements are present, you can apply the network theorem and other network analysis into the circuit. But as the nonlinear element is present into the circuit, you cannot apply this kind of theorem here. So the circuit further cannot be minimized, or the circuit cannot be analyzed with the help of this model. So though this is a good model, you cannot apply this model. So we have also discussed in this lecture the Ebers-Moll model. Ebers-Moll model, and in this model we have also mentioning that this model is very good because the four operating region of the transistor can be represented. With the help of this model. And the disadvantages is that I have said several times that it is the nonlinear element present into the circuit. So it is the nonlinear circuit model, and this is the large signal model. Large signal model means in the AC analysis we are always assuming that the small signal analysis. The large signal model means you cannot linearize the circuit. So as you cannot linearize the circuit, then there is a problem. So these are the thing summary we have discussed, the how AC analysis can be performed in any circuit, the steps towards the AC analysis in the previous lecture. And in this lecture, and the main part of the AC analysis is that replace the BJT with the equivalent model. Now replace the BJT with the equivalent model. We have studied a model here. That model is the Ebers-Moll model, and in the case of the Ebers-Moll model, we have seen that the some sort of advantages and some sort of disadvantages, but this is the starting point. From now onwards, with the base of understanding of the Ebers-Moll model, we will try to derive the transistor T model and with the help of this T model we will try to analyze the circuit better, because in the T model is the linear model. It is a non-linear model, but the T model is not the non-linear model, it is a linear model. So with the help of the T model we will try to analyze the further circuit, but that model is some sort of approximation. But you always remember that as there is diode present in the Ebers-Moll model, that's why it is called the non-linear model. But in the T model you will see there is only linear circuit element, and linear circuit elements is your passive element, that means the resistance, capacitance like this, and inductors that will be only present into the circuit. Okay, so from now next lecture onwards we will study this T model and analyze the circuit with the help of this T model. Thank you.